So as we was here talking about serverless lines, we saw how many AWS services impacts the latency of our microservices, and we very much one secret best practice that is the runtime. So the answer to the Rust always better. So this is the answer. But during this talk, we will not see Rust as a language. I am not a Rust developer, I use it, but I don't define myself as a Rust developer. If you want to see Rust in details, there are talks by Mamino, James, that is around, that's writing a book about. So this talk is more about Rust as a tool. So a tool to achieve lower latency and higher concurrency. For the people that don't know, I'm Daniele Frasca, working at Procedures at Sviga. He's a German TV broadcaster and is based in Munich. We are building streaming applications. So I am the leader of the backend. So we are serving users all across the German-speaking countries, and we have the needs of scalability. We have huge spikes. So we actually migrating from cluster to serverless because all our cluster cannot handle high traffic, even if you are putting 700 tasks to run. So we need to start with the basic. If you went in the look at the little talk, pretty much as I say, he did 40-minute talk, I can do it in 5 minutes. So practically, when we're talking about Lambda, we need to understand the left side. Lambda can only process one request per time. So the first time the request is coming in, the micro VM spin up, there is the init where the runtime, start the environment, download the code, and once the init is finished, there is the information of our code. This together is called start, and once this is finished, the Lambda is able to process second request, third request, until there are no requests and we shut down, right? That's it, this is the left side. So why this is important? Because when we are talking about Lambda, we need to have in mind some metrics, the concurrency and transaction per second. So the concurrency per Lambda can be calculated in this way, is the request per second per duration. Faster it is your Lambda, lower is the concurrency. And this will allow you to scale more. So that is the example with 10,000 requests per second. If Lambda running per second, you need 10,000 concurrent Lambda. If your Lambda running 100 milliseconds, you will only have 1,000 concurrent Lambda. So faster is your Lambda, lower is your concurrency. With this, we can talk about transactions. Luke has shown that this number is not 100% exact, but faster is your Lambda, higher is the transaction per second. So in this example, if the Lambda if you have 10 requests, the Lambda running 1 second, you have 10 transactions per second. If it goes to 500 milliseconds, you will have 20 transactions per second. So speed in Lambda is very important, and this also influence the cost of the Lambda. In fact, the cost of the Lambda is the allocated memory per durations. So all of this all good, and but how can we make it our Lambda faster? So we know, especially on the runtime, we can tweak the configurations. The most important metrics is the memory. So more memory you add to the Lambda, more power you add. But the memory, as we saw, also has an influence on the cost. What we can do more is changing the architecture. A lot of people use x86, but you can use ARM64. Usually give you 20% in performances. Always here, you can meet the young debugging one. He will tell you that you always need to double check. Sometimes RM is lower than x86. It depends really from what your code does. There are other little things that we can check. When you need to deploy smaller packages, you don't need to deploy the entire node modules or things that you don't need for running the code in productions. You need to initialize all your clients, connections, everything outside of the execution context. So in this way, the Lambda can reduce this part of the segment and so on requests. So a good practice would be avoiding the fat Lambda. Luca Manzanera actually has something to say about that. It's always dependent, but theoretically, the smaller is the Lambda, the smaller is the packages that you're deploying. You can use the temporary space that you have with your Lambda to hash something if you really need it, so that you can also reuse through the informations. And of course, you need to use parallelism and processing over sequential. This will make everything faster. Imagine that your Lambda process a batch of SQS messages. Instead of go one by one, you can do it in parallel. So all of these are the good practice that you can apply to any runtime, right? And why do that? It took 40 minutes, as we did it with 2 slides and 5 minutes. So this is all of these are the practice that we need to follow, right? Once you do this, you have only one problem: the runtime. So why we're talking about the runtime? I started many years ago with .NET, and when I moved to Lambda, the Lambda didn't support .NET, so I moved to Node.js with TypeScript. So because of this, actually a lot of us started using Python or Node.js. Node.js is one of the biggest runtime users, so in fact you see a lot of traffic and gigabyte for Node.js, but it's actually very, very slow. Node.js is one of the slowest, unless you're using Java, that is even worse. But yeah, Node.js is one of the slowest. And when you're actually building API and front-facing API, you need lower latency. Yeah, maybe Node.js is not the best choice. In fact, the best is Rust. No? Once you do it with Rust, you do it better. So, grand discussion on this. But why Rust? So when we're talking about Rust, a lot of people, also in the company, complain, no, we need to find now new developer, we barely know how to write code in Node, now we need to go to new languages, it's a disaster. But actually, we are there, right? So Rust is just different languages. So if you ask me to write Python, I have no idea. So it will take me time to learn the syntax. This is the same with Rust. If it is complicated, I guess, and if you want to build an operating system, again, but you will not use Lambda, right? So if you're like me, you're building small microservices for whatever is the reason, you can actually port your code easily in Rust. What you need to know to move to Rust are very few concepts. This is how I code usually my team. On top of this, when we're talking about Rust, especially the manager, it's not the time of writing code that we need to issue. We need to use the time to build the product, right? So when you write code in Rust, the code is compiled at runtime, so everything is already working. You don't really need to do extensive testing to find all the edge cases. So Rust forces you to build every single edge cases when you're using a couple of few types. And in time to make the product, Rust, we need to include the bug, we need to include the coverage. Once you write the code in Rust, because it's very limited languages, there are not many ways to do the same things like in JavaScript. So the code that you're shipping contains really less bugs and will accelerate the process of testing and so on. This is not coming from me, this is coming from Microsoft and Google, the white paper, the internet, you can read them about. So they practically, they found out that when they swapped to Rust, the developer initially thought that it took 6 months to onboard, but the reality was less than a month. Now, to build Lambda in Rust, what do you need to know? You need to know a few concepts. One of them is the most unlike, is called the ownership or the bug checker. If you are developing and you start coding, the compiler will give you a lot of levels. So practically, Rust is a different way to handle the memory, right? So although the languages usually allocate, every language actually, allocate something in memory, you use this allocated memory, and when you're finishing, this get deallocated. Rust, and so all of this is implicit for us. No? This is what is the garbage collector does. So when you're coding, you put a variable there, if this variable go to the heap, stack, you don't care, you get deallocated as a With Rust, you have three ways to initialize variables, and this will be painful when you start. It took me a good 10 days to get used to the virtual laptop out of the Windows. So, and one is to create a copy and pass it along. The other one is you just create a reference and pass it along, but you will get you just walk and you will get the reference back. And other one is to give up the ownership. All of this is cached while you are developing, and the compiler will give you 1,000 methods until you can make it right? Now, once you go over this and you didn't give up on Rust, there are really a few concepts. Struct and trace. We call in the languages, we call it class interfaces. Abstract, define custom data types with names and so on. Traits used to define shared behavior. In this example, I don't know if you can, in this example, I cannot read it here. We have two structs, the rectangle and circle, they implement an area as a trait, and each of this structure has its own implementation, right? So nothing new. So whatever you know in the other languages can be ported also to Rust. The other are enum and pattern matching. Enum pretty much is the same as the structure, but allow you to achieve more with less code. For example, you can implement a different type of variants, now with different signature, something that you will need multiple structure to achieve the same goal. Pattern matching is what we call switch, but is a bit more powerful. You can decouple the structure, tuple, structure, array. You can do pretty much everything. Also here, the code is very simple. You can see how enum and pattern matching are used together. In the main, you initialize the two classes, the enum with the rectangular circle, and you are finding the area. In the area implementation of the structure, the implementation of the enum, you have this method where you have the switch, and based on the variant, you apply some code. Yeah, nothing major. The only two concepts that you need to know are option and result. These are usually usually many languages use null, nil, undefined to represent empty values, or exception to handle errors. Rust has a completely different approach, because they want to skip the issues of null pointer exceptions. This is very important when you're building operating system, this kind of stuff. And they want to avoid sensitive data leakage through exceptions. So they have these two types. An optional value can be either something or nothing, and the result can represent a success or an error. Very simple. And here as well, the code is very similar, very simple. We have if-else. If we find the first character, we print it. Otherwise, there is none, and we print something else. And for the match, we try to do divisions. If succeeded, we show the result. Otherwise, we have an error, and we handle the error. That's it. With all of this, actually, you can build any prototype with Rust, because this is all you need. There's a bunch of if, else, and the loop to write single responsibility lambda. So it's very simple. Now, prototyping or writing code with Rust is a bit more verbose. So I start with .NET 1.0. So, and to me, it looks like what I was doing 20 years ago. So I'm old. But it's very good. So once you start, it forces you to
to cover every single conditions. And because you're covering every single conditions, in the end of the day, when the code compile, you kind of shipping a ready production ready code, right? So that's it. This is everything about Rust. Now, 1 second. Hop. 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 Okay. So now, why we need to do Rust, right? So what is the investment? What are the benefits of using Rust? Let's take this basic microservices, API Gateway, Lambda, DynamoDB, right? This is the hello world of AWS. In the Lambda, maybe there is a bunch of if-else, some condition that make needed. Otherwise, you could use the VTL as integration with DynamoDB. So again, Rust, one of the fastest, Node.js, one of the slowest. So if we are going to compare, this is what we are seeing. So at the same memory settings, we know that Node, a lower memory setting, is very slow. And sadly, there is still a lot of people that are using Node very low memory settings. But this comparison, to me, I think is the wrong one. But a lot of people do this kind of comparison. And if you're comparing memory per memory, the same code, we see that Rust overall, on 2.5 billion executions, is 35, it's more than 30% cheaper. But again, this is not the right way to do it. In the cold start, we see a completely different scenario. Rust, more or less, is always very stable, while with Node, you will die at some point. 128 megabytes, waiting to run. Cold starting, actually, in serverless application is not a big problem. So if you have a front-facing application with constant load, the cold start usually is less than 0.1% of your total invocations. Of course, faster is your function, lower also the cold start. And here as well, in the cold start, it's cheaper, but we are talking about dollars, right? So it's not really important. So what we really need to do a fair comparison is running a tool to find the sweet spot of your Lambda. There is the famous Lambda power tuning that will give you the best setting for your Lambda. Usually with Node.js is 1 gig of memory. So even the cost of having the Lambda running at 1 gig of memory usually is the same as, is even better if you have lower setting in the memory, because lower is if you remember, the cost is allocate memory per duration. So giving power to the Lambda will reduce the durations, and overall you will have way better result. Even if you're, and I invite you not to check how much memory you use, because this is not a good parameter for Node, because if you're using 1 gig of memory, maybe the matrix will give you, you're using only 20. So you are tempted to move to 128 megabytes. But this will just make the overall duration of your Lambda worse. So now, we did our power tool tuning on the Lambda and everything. We know what is the sweet spot for each of the invocations. The real comparison is actually Node.js at 1 gig of memory and Rust at 256 megabyte. As you can see, the test case, this is one of my old services that was running, and doing the swap from Node to JS gave us practically 3 times more scalability for the same service and a save of around 37%, but way more on speed. So overall, we can do more with less. Now, we can argue, right? You don't do 2.5 billion executions. It's okay. So so let's imagine that you have 1 million, 5 million. So if you have a front-facing applications, you will be on this target. As I said initially, I am the team leader of this backend API behind the streaming applications. So the streaming application is like Netflix, this kind of stuff, right? But for the German speakers. So even if we don't have the load of this big streaming application, we still have millions of Germans that look at the German's content. As you can see here, Rust always come up around 45% cheaper. You always hear around, especially from AWS, that if you have constant load, you should move to the clusters, right? So there is a kind of formula that you can apply to know what more or less, how big is your cluster, and is, I wrote it, because I always forget, is request per seconds time the task durations. So now imagine 10 milliseconds. So to run 100 millions of requests, you need, that is more or less 1,100 requests per second, if you spread in a day, you will need a cluster with 12 virtual CPU. So that theoretically, if we are going to put this cluster up and running, it will result in 3 tasks with 4 virtual CPU, 8 of gig of memory, running the entire day. You can handle all of this, and it will cost theoretically less, like $500, right? So it will be even cheaper than Rust. But what we never consider is that now the cluster needs the VPC configurations. You need the application load balancer. If your code, for some reason, does some external call, you need the NAT gateway. I do multi-regions, so you need to duplicate everything in another region, and all of this will give you a total cost of ownership way higher than migrating your Lambda with Rust, or it will be very close to actually the cost of Node. So serverless is expensive at a certain level, but if we are we shouldn't compare Apple, what is this? Apple for Apple, Apple for Orange, whatever, right? So it's not, we are not playing on the same playground. Now, fantastic, we see, still Rust, I don't want to convert it. 1 year ago, they announced this Las Vegas, LRT, right? Low latency runtimes. There is a crazy guy that he was in productions with this already last November for very specific functionality. Now, this is an option. What is this LRT? If you don't know, it's practically is a new runtime rebuilt from the ground up. They are using QuickJS. There is a Node compatible API and use pretty much Tokyo, and many API are written in Rust to make it faster. So the key here is this runtime is very small. It's, I think, under 5 megabytes compared to the most generic runtime, like Node, that are around 50 megabytes. How it works? Apparently, the JavaScript code is compiled in bytecode. The bytecode is compressed in LZ compressions. And all of this gets shipped with the executable, and now, thanks to the QuickJS engine, they can actually run it faster without downloading extra JavaScript file. Oh, good, right? So, to be honest, how this works under the hood, I don't care, but there are people they want. For me, this is another tool in my arsenal. So why I'm saying this? Because, of course, LRT, it does not work for every use case. I think is ideal only for very small serverless functions. Imagine now you have a step functions with a lot of lambdas that they are doing very small things, perfect scenario. Real-time processing, authorization, validation, or as I use especially as a companion of my Node.js Lambda, I have lambdas that, I don't know if you're aware of a claiming check-in pattern. Practically, I get events from Kafka, and this through travel through the pipe enhance with a Lambda, and I take this payload and upload it to S3. This is just a wrapper around the AWS SDK S3 API. And so this is a perfect scenario. While with Node, the same Lambda was running maybe in a couple of 100 milliseconds, and now is very low. I get the performances of Rust. But also this one, as you know, this is in beta, it's experimental. I should say officially you should not use it in productions, or at least do it without saying to your manager. But there are a lot of libraries that are not supported. So the idea of the AWS team is not to replace Node. So this is not a drop-in replacement. It's just for specific use case, for specific API. And it's very simple to use. If you are in Node, for example, this is AWS SEM, right? So pretty much it's the same. The only difference is the runtime and the memory size. So why I put 256 megabyte? Because once you're running Power Tools tuning, you will see the sweet spot, and usually it's between 128 and 256. I think 256 is the best one, even if all the other examples that you will see around go with 128. So you have two ways to use this new runtime. One is to use the custom Amazon Linux 2023 and package with your JavaScript file, or using the layer. I use the layer, that is way simpler for me. But the key here is it's easy to use. My developers, we all doing a Node, so we just try out. If it works, fine. If it doesn't work because we don't have some library that is not compatible, we didn't waste a lot of time, and we just reverted. And at this point, we can decide if we want to rewrite in Rust and invest time, right? So this is the key. LRT doesn't make you waste time on the try. Now, this is the AWS team, the official things as well. As you can see, to me, they are doing the wrong comparison. The reason why they do this comparison, where taking the memory settings the same, is because a lot of people, and I can tell you as experience with my developers, they are starting the Lambda with 128 megabyte and start complaining. I was better before with Docker, now I put it there, it doesn't work, it doesn't scale, and everything. But this is not the way. So every time that you are working with a specific runtime, you need to know your configurations. Java, for example, to have decent performances, you need to be at 3 gig of RAM, right? So of memory. Node, 1 gig. If you're going outside of this best practice, you will have a cold start of 1.5 seconds. This is why I believe doing this comparison is not a very good way to do it. So, again, now, Rust, we know that is the best, but Rust is also a new language that we need to learn, that we need to sell to our managers and everything. LRT is there as a very similar comparison, very similar performances of Rust. So you will get all the benefit out of the box with just tweaking the same configuration that you're using with your Node.js Lambda. Pretty much we finish. I think I did it too fast. So this is the key. We are nowadays, once we are working with serverless, we need to really know what we are doing. So each AWS services has a different latency. This can have an impact with our microservices. The runtime is one of the best practice. They don't tell you because it's very difficult to change. You need to put some capacity. You need to invest time. But we have a choice. And the choice is this LRT component that is still in beta, but is pretty stable if you're doing the basic. We're using around the AWS SDK. Now you can even bring your own library, extra library of the SDK. So the key of working with serverless is to really tweak and use the best practice and use whatever tools we have. Moving to Rust takes time, but I never say that you need to change the entire ecosystem. It's just a specific Lambda. We, at ProSieben, we have, especially on the backend, thousands of API. We have key API that need to work at very low latency for what low latency can be. And sometimes we are moving, I know, we are removing SQS, we are preferring kinesis, a certain type of scale. And with the code is the same. We are starting slowly but steady, just converting everything to Rust where it makes sense. And in a microservices, usually you have front-facing API and background process. The background process for facility, to keep our life easier, are still in Node.js, the API moving towards LRT or Rust. And that's it. This is my take on serverless. Just you need to really know what you're doing. Just not drop something there, put provisional concurrency, and hope that everything is magic. It will not work. Thank you.